So yeah, the goal of today's lecture is basically trying to cover the remaining steps from having a catalog of galaxies to extracting cosmological constraints from that catalog of galaxies. And there's a lot of, this is a very technical aspect of the analysis, is the main technical aspect of the analysis. So what I'm only going to give you broad strokes of what it entails, right? But I won't be able to go into a lot of detail, so what I'm going to show you is a simplified version of how this actually works in practice. So it will give you an idea of how it works, but there's a lot of more technicalities on how you actually take a catalog and analyze it. And the best way to learn about this is to actually go through papers of existing analysis and see what all the nuisance is that people need to deal with when you have to analyze galaxy data. It's inherently messy, and there's lots of like tiny details that you need to take into account. But this is kind of going to give you the main, the broad picture of what we're trying to do. All right. So okay, maybe let's start from the end. Ultimately, what we care about is we want to constrain some cosmological parameters. I'm going to call those Q. Right. So Q is some set of cosmological parameters, omega m, sigma 8, but also any other model parameters that we need to describe our data. This could be galaxy bias, for example. We talked about other nuisance parameters, for example, the multiplicative bias we talked about yesterday in the Q&A. So any other free parameters of your model, right? And what you want to do is to, from some data, you want to learn something about these parameters, right? You want to know what their value is with some uncertainty. So ultimately, and not only that, but in cosmology, in most cases, the only thing you will have is a single data set and not ways of simulating that data set very often, right? Sometimes you might, but often you just have a single data set. You only have one realization of your data, not many. It's not like a particle physics experiment where you can just have more events and more events and more events and use those to estimate those parameters, right? Here you have a single event, which is the universe. So how do we infer cosmological parameters from a single event? And so the idea here is to use Bayesian statistics. And Bayesian statistics is kind of a different philosophical way to think about probability, right? In this case, the idea is to treat your parameters, the parameters that you want to estimate, as stochastic variables. And the probability of those stochastic variables is basically the degree of belief that you have that these parameters take a given value, right? And this is the degree of belief you have based on the data that you have available to you, right? We know that whatever the parameters of the universe are, according to the naive lambda CDM model, are not actually a stochastic variable, right? They're whatever they are. But the Bayesian picture for probability tells you that you should think of them as a stochastic variable because it's contingent on the data that you have available to constrain them, right? So ultimately, what we want to characterize is what is the probability of measuring some parameters given our data. It's this conditional probability, okay? So this is what we call the posterior probability distribution of our parameters given our data. And if we use Bayes' theorem, which I'm guessing many of you have seen in your statistics classes, right? What this is the probability of our data, of having seen the realization of our data that we see, given those parameters, multiplied by the probability of the parameters, independent of any data, divided by the probability of our data for any value of the parameters. Okay? So we said this is the posterior distribution. This is what we call the likelihood function. This thing here we call the prior. So the prior basically tells us what, in the absence of any data, do we think or do we believe about these parameters, right? Do we have any prior information about these parameters, for example, from preceding experiments that have nothing to do with this data? Or are there physical considerations that we need to take into account? For example, it doesn't make sense for sigma 8 to be negative, right? So that's what the prior is supposed to encompass. And then this thing here is called the evidence. And you should just think of it for the purposes of what we're going to talk about as a normalization factor, right? We care about this probability distribution, and all probability distributions just need to integrate to 1. And this doesn't depend on Q, right? So it's just some normalization factor. We don't care about that. We will always be able to renormalize our probabilities, okay? The main thing we care about is the prior. And the most important thing, actually, is the likelihood, right? How do we characterize the likelihood of our data? Right, okay, so let's start with some ideas. How could we write a likelihood for our data, right? And first of all, maybe we need to define what our data is. So let's look at a simple case where our data is a Gaussian map, right? We already said, for example, that according to lambda CDM modulo inflation, the temperature of the CMB is a Gaussian random field, right? We know that it follows Gaussian statistics. All right, so let's say that our data is just the value of some map, which we know is Gaussianly distributed at different positions in the sky. All right? All right, so if we know that the map is Gaussianly distributed, then the likelihood function, the probability of our map given some parameters, is just a Gaussian, right? So in this case, the likelihood would be P of B given Q, would be multivariate Gaussian 1 over the determinant, square root of the determinant of 2 pi times C, where C is the covariance matrix of our data, the exponential of minus 1/2, A as a vector, or D as a vector. Well, let's say A. So A is the same as our data, right? So it's just our map, and we're going to construct a vector from it. Each element of the vector is just the value of the map at a given pixel in the sky. A transpose C to the minus first A. This is the general expression of a multivariate Gaussian. Now the question is, where are the parameters here? And the parameters are in the covariance matrix, right? This is where the parameter dependence comes in. What is the covariance matrix? Cij. By definition, this is just the expectation value of A in pixel I with A in pixel J. And we've already seen what this is, right? This is what we call the correlation function for the field A at angular separation theta ij, right? The angular separation between these two pixels in the sky, right? And we know that this thing depends on cosmological parameters, right? Because we could connect it with the power spectrum. You know, psi of theta, remember, was sum over all the multiples, 2L plus 1 divided by 4 pi, Legendre polynomial of cos theta times the CL of our data. And the CL depends on cosmological parameters. Okay, so in the case of a Gaussian map, we could construct a Gaussian likelihood where all the parameter dependence is encoded in the covariance matrix, which appears both here and here. And that would be the end of it. But this is problematic, right? It is problematic mostly because we need to calculate this thing. And calculating the correlation function itself is not a problem. What's a problem is having to compute the correlation function for all pairs of separations between pixels, right? So if we have n pixels, and this can be many hundreds of thousands of pixels, then calculating that correlation function is an n squared problem. So that's going to be quite slow, because we need to do it for every pair, right, so that we can stick it in this formula. That's going to be a big-ass matrix we need to compute and store in memory. And then we need to invert it, which is even worse than that. So inverting a matrix of size n by n is an n cubed problem. So it becomes extremely expensive, right? And presumably, we want to do that for different values of the cosmological parameters. So every time we change that value, we need to recompute this matrix, and we need to invert it. And that's a pain in the ass, okay? So this is not a practical way of analyzing a Gaussian map, unless you're just interested in the largest scales, in which case maybe you can make a very low resolution map with just a few pixels, and then all of this becomes a lot easier, right? But in practice, this doesn't work. However, we did say something, right? And sorry, and where's the problem here? The problem starts from the fact that our data is super large, right? Our data is many, many pixels. But we already said something in the first lecture, which is for a Gaussian random field, all of the information is encoded in the power spectrum. So maybe what we could do is, instead of using our map, we just compute the power spectrum of our map and use that as our data, because the power spectrum will be a lot smaller in size, right? So maybe, maybe that's the way to go. All right, so let's leave that idea lingering in the back of our minds, and for a second, let's stop talking about statistics and let's talk about power spectrum estimation. So how do we actually estimate power spectra from the data? All right. So in Manu's lectures, and I think I've also mentioned this, we already wrote a very simple estimator of the power spectrum using the ergodic theorem. And this works if you have a full sky map of some quantity, right? If you have that full sky map, then you can compute the spherical harmonic coefficients of that map. And we said that the variance of these harmonic coefficients is essentially the power spectrum. And the power spectrum only depends on L, so we have equivalent modes for all the different M's corresponding to the same L, so we can average over them. So this was the idea behind the ergodic theorem, right? So we take that, we square that, sum over all possible values of M from minus L to L. How many of them is that? Well, that's 2L plus 1, because you also have M equals 0 here. So divide by that. And this is your estimator for the power spectrum. Putting a hat on anything that it's an estimator, meaning some combination of data. So there's no parameter dependence. There is just some combination of our data. Okay. Okay. Well, that sounds easy. However, this is difficult, right? Because we need to calculate the spherical harmonic coefficients of our map. That in itself is not difficult, but that means that we need to do some kind of harmonic transform of our data, which means an integral over the full sky. And we never have observations over the full sky, right? We always have observations over some region of the sky. We can never fully cover the sky. If anything, because you have the galaxy, the Milky Way, in between us and the rest of the sky, right? So we always have data over a region of the sky, and that effectively means that we have masked data, right? So let me write A tilde as the map that we can actually observe, right? The masked version of our sky. All right, so how can we write this? We can write this, for example, as the true map of the sky over the whole sphere times what we call a mask, which will tell us whether or not we can actually observe that part of the sky. So this mask will be 0 if there's no data, or 1 if there's data, for example, in the simplest case. Okay. Okay, but so what happens if we then apply this estimator to the masked data? Well, the first thing we need to do is to compute the spherical harmonic coefficients of this thing. We would need to do ALM tilde. And remember that a spherical harmonic transform, you can think of it as a Fourier transform, okay? So what happens when you have a Fourier transform of the product of two different quantities? What is that? It's the convolution of the Fourier transforms of both quantities, right? So this, without writing the actual equation, this will be the Fourier transform of our map, or the harmonic transform of our map, convolved with the harmonic transform of the mask. Okay? In harmonic space, convolutions are a bit weird, so they look like this. They look like sum over LM prime and LM double prime of some kernel. This is the convolution kernel on the sphere, so it depends on L prime and L double prime, and M prime and M double prime. This is something called the Gaunt coefficients. If you have seen them in quantum mechanics, if you haven't, don't worry. It's some kernel, doesn't depend on anything. It's just pure math. Of the W LM double prime and the A LM prime. Doesn't really matter what the Ghosn coefficients are, what this is telling you is that the spherical harmonic coefficients of your masked map at a given L, they receive contributions from the spherical harmonic coefficients at other L's, L prime here, right? So you have mode coupling or mode mixing. So for a given L, you're actually receiving contributions from several other L's, okay? This is similar to what we said CMB lensing does to the CMB map, right? We have mode coupling caused by the fact that we take their temperature fluctuations and multiply them by the gradient of the lensing potential. That gave rise to mode coupling. Back when we discussed that, that was a good thing because that meant that you could use that to recover the lensing potential. Here, we could use that to recover our mask, but that's not very useful because we already know what the mask is, right? So that's kind of pointless. So here we have to deal with mode coupling. Now so let's say that we take this and we stick it in this formula. The result is going to be basically a convolution as well, but now in terms of the CLs. So what you'll see is that if you do that math, your estimator of the CL is going to be a sum over other modes L prime of a matrix that we call the mode coupling matrix, LL prime, of the true CL, CL prime. And this mask here is, sorry, this mode coupling matrix depends only on your mask. It doesn't depend on your data. It's only caused by the kernel, the window function that you have for your observations. Right. This is called the mode coupling matrix. All right. So a priori, this doesn't look too bad, right? Because if you can compute this mode coupling matrix, this is just a matrix. You invert it, you put it on the other side, and now you have an unbiased estimator of your power spectra, right? So the recipe then would be, we take our masked map, we compute its spherical harmonic transform, we stick it in the naive power spectrum formula, and then we remember that there's mode coupling, so then we just invert the mode coupling matrix and multiply by it. And in principle, we're done. So this is the basis. What I just described is what we call the pseudo-CL estimator of power spectra, okay? And it's based on one interesting result, which is the fact that MLL prime, so the mode coupling matrix, can be calculated analytically. This is not surprising because we could always, if we do math, we could write this mode coupling matrix in terms of these Ghosn coefficients. So it's not surprising that we can write an analytical formula for the mode coupling matrix. What's surprising is that we can do this very quickly. So the analytical calculation leads to lots of cancellations that make the calculation of the mode coupling matrix very fast. So yeah, so this is one of the ways in which we calculate power spectra or estimate power spectra for real data. The main complication is accounting for the mode coupling due to incomplete observations in the sky. Okay, and I haven't written any equations as to what this mode coupling matrix looks like, or anything else, right? But those expressions exist. Look at my paper. So there's a paper called Unified Pseudo-CL Estimators. I think that's what it's called. By me. So if you Google that, you'll find a paper where all these formulas are written in detail. Yeah. Yeah, so that's a good question. This estimator doesn't assume anything about your map. It doesn't have to be Gaussian, right? Mm-hmm. No, So those cancellations happen regardless of the statistics of your field. They don't need to be Gaussian. They just need to have a 2-point correlator, and that's all. But all fields have 2-point correlators. Yeah. Yes? The mask is a simple map, right? It's the same. So the second half of this lecture, we're going to go through a notebook that will take us for a real data set all the way to parameters using all this. So we'll see a picture of this mask, for example. So it's literally just a map. Cool. Yes? You will lose some information. You always lose information because you don't have that information to begin with, right? This mask prevents you from seeing some parts of the sky, so you will always lose some information. And the way you lose it, in terms of the power spectrum, is that now your power spectra measurements at different L's, they will be statistically coupled from one another. So you will not be able to extract all of the information from a given L because it will be coupled with adjacent L's. Yeah, so that's how, yeah. So what you will recover, so this estimator, once you invert the mode coupling matrix, when we say that the estimator is unbiased, what we mean is that if we applied this estimator to many realizations of our data, and we took the average over those many realizations, then the result would be the true underlying CL that generated our data, basically. Yeah. Of it does that automatically, right? Because all what you call edge effects are basically incorporated in this kind of coupling kernel. So yeah, that all happens automatically. Yeah. There are nuances in here when you want to do, for example, things called mode purification, where you want to enhance the estimator a little bit, where you need to take some edge effects into account. But for the naive estimator, that's, yeah. Yes. And we'll see an example of that when we look at the. Exactly. This window function doesn't need to, or the mask doesn't need to be a binary function. It can be whatever, right? That will only change the form of the mode coupling matrix, but that's fine. Yep. Yep. There's no assumption that this has to be binary in this. Yeah. Just needs to be the multiplication of two maps. It doesn't even need to be positive definite. Yeah. All right. So now we have a way to estimate power spectra from real data. How is it useful, right? Because we started from, we have a very well-written likelihood for a map, at least a map that is Gaussian. Remember that the large-scale structure is not Gaussian, so this doesn't even help that much. But let's say that we're in the Gaussian case. Why is it useful that we calculate the power spectrum? We now still need to calculate the likelihood of this power spectrum, right? But it turns out that that's really easy. And that's the fact that we can just write a likelihood for the power spectrum is enabled by something called the central limit theorem. Anyone familiar with the central limit theorem? Some people are. Okay. Most people are. Okay. I was not familiar with the central. I didn't study any statistics during my undergrad, so I was not aware of this. But it's this magical thing, right, where if you're trying to calculate the probability of this particular combination of random variables, which is a mean of random variables, right? So 1 over n sum over I of xi, right, where I goes from 1 to n. So what I'm writing here is, imagine that you have a bunch of stochastic variables, xi, with whatever distributions you want. They can be top hat distributions, they can be log normal distribution, they can be whatever, chi-square distributions. But they all have the same mean, right? So if you have any variable with the, so a bunch of variables with random distributions, and you calculate the mean of them, this probability distribution in the limit, when n goes to infinity, will converge to a Gaussian, it will go to 1 over square root of 2 pi sigma squared e to the minus 1/2 of x minus mu divided by sigma squared. All right, where mu is the mean of these distributions, right? Yeah. So why does that help us? It helps us because what is the CL, right? The CL for a given L is just an average of the ALM squared for all the M's within that L, right? So so this is what I'm calling N, right? 2L plus 1 is basically N. So if L is large enough, then the distribution of the CL should be Gaussian. And then we can write the likelihood for the CL. So here's an example. This is something that you can do very easily with just, this was literally 4 lines of Python. So here, what you're seeing is so I've generated a bunch of Gaussian map realizations, computed the power spectrum for all of those Gaussian realizations, and then this is the histogram of the value of the CL at L equals 2 for all of those realizations. There were 10,000 realizations, okay? And you can see that at L equals 2, and then, and the black line is a Gaussian function with the same mean and width as the other distribution. You can say that at L equals 2, the distribution of the CLs is definitely not Gaussian. You can actually write for a Gaussian map that this distribution should be a Wishart distribution, whatever. But then as you go to higher Ls, you start seeing that it starts converging more towards a Gaussian, right? So at L equals 60 is definitely a Gaussian. Usually, if you have full-scale observations, at L equals 30, you're probably close enough to a Gaussian. Okay, so if you're worried about very large scales, then you should probably be doing this kind of likelihood, a map-level likelihood, because that will not be too expensive. You won't have too many pixels. But for the most part, a lot of the information we get from large-scale structure comes from relatively small angular scales. And in that regime, the power spectrum likelihood is just a Gaussian. So we're going to use this as the likelihood for our data. So our data now is going to be a bunch of CL measurements. And our likelihood will be proportional to the exponential of minus 1/2. Then we can sum over all our different power spectrum measurements, LL prime, our measured CL, minus the theoretical prediction for that CL at the value for the cosmological parameters, times the covariance matrix of our measurements, LL prime inverse, and then CL prime measurement minus the theory prediction CL prime at the cosmological parameters. Okay, so this is going to be our likelihood. Okay. There's an ingredient in that likelihood that I haven't talked to you about, which is the covariance matrix of our measurements, and how we actually estimate that covariance matrix. There's different ways of doing that. Ask me later in the Q&A if you want to know more about that. Okay. Okay. Right. We have a likelihood function. From that, we can construct the posterior distribution, which we just saw before. How do we extract information from that posterior distribution? All right, so let's imagine that we have, so the problem now is parameter inference, right? How does that work? So let's imagine that we're in a very simple case. Our model has a single parameter Q, and we have a function that we have written in Python that tells us what the probability of Q is given the data. Well, then what you do is you just evaluate this function for several values of Q. It will probably look something like that. And then you can calculate the confidence intervals, right? So around the mode of your distribution, what is the interval that contains, let's say, 68% of all the probability? What is the interval that contains, let's say, 95% of the data? Sorry, of the probability, etc. Right? So this would be what you call the 1 sigma confidence interval or the 2 sigma confidence interval for that parameter. Okay, that's very easy if you have a single parameter. All right. What do we do if we have more than one parameter? And in usual likelihoods, you'll have at least like 4 or 5. Normally, for large-scale structure, because we have so many nuisance parameters, all these bias terms, multiplicative biases, things like that, you can end up with several tens of parameters, so 20, 30 parameters. What do we do in that case? If we had 2 parameters, maybe we could do, a grid, Q1, Q2. We sample the parameter space in a grid, evaluate P at each point in this grid, and then do the same. But now we will have to deal with 2-dimensional integrals instead of 1-dimensional integrals. Fine, maybe we can do that. It's kind of annoying because a priori, it might be that you do this and then you realize that actually the probability distribution is concentrated here. So then you've thrown away all of these computations for nothing. That's kind of annoying. And this gets worse the more parameters you have, right? So here we have, if we've divided each dimension here in n, you have n squared grid points at which you need to evaluate your function. If you have 10 parameters, then you'll have n to the power of 10 points at which to evaluate this. So very quickly, this becomes completely untenable, right? You can't even store that many values in a computer. If you have n equals 10, let's say 10 to the 10 is a huge number. So we need to do something, right? This is called the curse of dimensionality. And the standard method to deal with that is, well, there's many different ways, but many of them basically revolve around this idea of Monte Carlo Markov chains. So the idea in a Monte Carlo Markov chain or an MCMC is that instead of actually evaluating the likelihood and then doing integrals of that, what we will do is we will draw samples of this likelihood. So we will not do a grid like this. Instead, we will generate samples of the likelihood. And those samples will tell us where the likely values of our parameters are. Okay? So the most common way of doing this is something called the Metropolis-Hastings method, and I'll just mention that briefly. And then we will move on to actually doing things in practice. All right. So let's say we have a likelihood with just 2 parameters to make it simpler, Q1, Q2. All right. So the first step is to just start somewhere, right? Pick a first sample. Let's call that Q0, for example. So you pick a value. Usually you would pick a value that you think is close to the maximum of your likelihood, so something that fits the data, more or less. All right, then you propose a new value. And you do this by sampling from a different distribution that we call the proposal distribution. So I'm going to call that G. And G is going to be a probability distribution for Q1 given Q0. So we're going to draw from this distribution. Usually what this will be is a Gaussian function, right? It's a Gaussian function where we say, OK, we start from here, and we'll draw another point around this point with a probability distribution that's a Gaussian, right? So it will be very unlikely for this point to be very far away. So it will probably be somewhere around here, OK? So take another point. Let's say this is Q0, this is Q1. Then we calculate the 2 probabilities, right? The actual probabilities, the posterior distribution, right? We calculate P of Q0 given the data, and P of Q1 given the data. In fact, let me write the other way around because it's going to be better. So P of Q1, P of Q0. All right, so we take those two probabilities. What we want to know is, with this jump, have we gone somewhere more likely or less likely than before? Because we're moving towards less likely points, then that's not good, because we're going to start sampling regions of the parameter space that we're not very interested in anyway. So what you look at is the ratio between these two. I'm going to call that alpha. And if the new point is more likely, then it's more likely. That means that it's closer to kind of the maximum of the probability distribution. All right. If we just accepted this point just because it's more likely, then the only thing we will achieve is going towards the maximum, and we don't care about that, right? We care about sampling the whole distribution rather than just going towards the maximum. So instead, there's an extra step we take here, where we now draw another random variable, u, from a uniform distribution in the range 0 to 1, for example. And then we ask ourselves, is u smaller than alpha? So for a number between 0 and 1 to be smaller than alpha, this will be more likely if alpha was a large number, right? So this will be more likely if the new point is more likely than the old point. So if so, then we keep Q1 as the new point in our random walk. Otherwise, if u is smaller than alpha, then we keep the original point, Q0. Okay? Now, because u can be a small number as well, this will allow you to actually choose points that are less likely than the previous one, but not too many of them, right? That's roughly the idea. And that's it. And then you go to the top, you replace Q0 with the new point, and then try again, try again, try again. And you start making a list of points, right? Q0, Q1, Q2, et cetera, et cetera. And you build a chain based on that, and that chain will be a random walk in the multidimensional parameter space. This is an example of how this works in practice. This is for a single dimensional distribution. So the black curve here is the posterior distribution you're trying to sample. The red curve is the proposal distribution, so this Gaussian here that we use to select new points. And this is just, jumping through different points in the likelihood and then rejecting or accepting one of them. When it rejects something, you see that the red point, which is the new one, is a cross, and then you just keep the blue point, which was the previous sample. Okay? Now, why is this useful? Because then imagine, I don't know, once you have a chain of points drawn from this posterior distribution, then you can calculate, for example, what is the mean value of your parameters. Well, that's just sum over all the points of Qi divided by the number of points in your chain. You can calculate the variance. You can calculate any statistic that you want from that chain, right, for your parameters. All right. So this is the idea, right? So we know how to compute a power spectrum. We know that for power spectra, unless we're interested in very large scales, likelihoods are Gaussian. And now we know how to sample a multi-dimensional posterior distribution. So in principle, we have almost all the ingredients we need. Yeah. This is what you can compute, right? Remember that P of Q given D is just P of D given Q, which we just said is going to be a Gaussian distribution, right? Times the prior, which you kind of decide what your prior information is. In the example we're going to see, I'm going to assume that I don't know anything about my parameters, so this will be just a constant. And then, well, the normalization, P of D, right? So in this case, unlike what Paco likes to do, which is a different way of sampling parameters, called simulation-based inference, in this case, we can actually calculate the likelihood and the posterior distribution. It's just that our posterior distribution depends on too many parameters, and it's difficult to do multidimensional integrals to calculate confidence intervals, right? So this is a faster way of doing that. Yeah. I think he was first, and then, yeah. Yep. No, that's not a problem because this is precisely what you want, right? So the probability, so the number of points you sampled in a given region will be proportional to the probability of that region. So you actually don't want to sample it very, very often. This method mathematically guarantees that the resulting set of points follow the original distribution. So you'll have more of them towards the center and fewer of them towards the edges. Yeah. 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 You would, so for most cases, and we'll see an example here, you would probably throw those away. There's many reasons for that. Usually, well, very often they won't contain that much information depending on what parameters you're interested in constraining. And we will see an example here where very often the lowest L modes are contaminated by systematics. So you just end up throwing them away. We talked about that a little bit yesterday when we talked about observational systematics and how they can contaminate your data, right? Most of these systematics are, for example, we said dust from the galaxy. The galaxy is a very big thing across the sky, so it dominates on large scales. That's why large scales are usually dominated by systematics. So very often you just throw them away for large scale structure, yeah. But you know, Walter, for example, works on some things that where the observable actually lives on large scales, right? The thing you want to constrain, non-Gaussianity in this case, lives on large scales. So in those cases, you need to worry about the likelihood not actually being Gaussian. I haven't discussed how to deal with that, but there's ways of dealing with that. Yeah. 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 It's difficult, right? So these are really tricky distributions, right? In 1D, it would be a distribution that is bimodal, right? That has two maxima, for example. And one of the dangers of Metropolis Hastings is that you might start here, and then it will only sample this, and it will never take any samples that are accepted in this point, right? Because, yeah, you can only allow for this if your proposal distribution is very broad, but then you're going to be rejecting lots of samples. So it's yeah, so in the case of multimodal distributions, there's different ways of going about it. One of them is to run several chains. So you run several MCMC chains starting from different points. So you could, you know, imagine starting one here, one here, one here, one here. Many of these will converge here, but some of them will end up converging there. So there's one way of, you know, trying to account for these things. This is the simplest way. And then there's other, Metropolis Hastings is the simplest version of MCMC. There's other ways of sampling that allow you to potentially cover these points, right? I'm not going to go into the details of that, but there's, for example, what's it called? I forget the name, something annealing, where effectively what you do is you take your probability distribution, your posterior distribution, and modify it by giving it some temperature that effectively kind of equalizes these two peaks. So it will make your posterior a bit more more homogeneous, let's say. That's not great because this is not the thing that you want to sample. But what it will allow you to do is to start gathering some samples that cover the whole region of parameter space, and then you remove the temperature and go back to this thing. But still, you already have some samples in the right region, so then you can actually end up sampling the right distribution. There's different techniques, but as you say, this is the kind of pathology that you need to be aware of when you run an MCMC. There's other pathologies when, you know, in 2 dimensions, if your model has a complete degeneracy between 2 parameters, your probability distribution might look very complicated like that, right? Because there's this region of parameter space that is that can be explained by either a given value of Q2 for a given value of Q1, or, you know, if you have parameter degeneracy, sampling this can be annoying. So the simplest distributions will be the ones that are very well contained, like that, right? And MCMC will always work in the simplest case. But if you have multimodality or strong degeneracies, then things will be a bit trickier. all of that. All of that. And so if you, and it's interesting, and this has to do with the prior, right? So if you reparameterize your theory in a different way, let's say that you had a theory that was dependent on your parameters like A and B times some template or something like that. That was your model for your data, was A times B times some template, plus A, for example, or something like that. If you do that, but then reparameterize, so you sample this model, and let's say that you do it again, but now you say, this is stupid. Why do I have A in both places? Instead, I should be sampling a parameter here that I'm going to call A, and then another parameter here, right? Let's say you do this, right? Get your chain for big A, and then from your samples of A, you just divide by your sample of small a, and get B, okay? The distribution of B in this chain and in this chain, they will not be the same. Because you've assumed, in one case, that you have a flat or whatever prior on this big A parameter, and in the other case, you'll have assumed that you have a flat prior on the B parameter, right? And that might have, if your data is not very constraining, you will end up with a posterior distribution that doesn't look the same in both cases. If you cannot decide between one and another, that will only be if your data is not constraining enough, right? So if your data is not constraining enough, you're going to be dominated by your prior. In that case, I don't think you should make any strong statements about the values of these parameters, because they depend on your prior assumptions about those parameters, right? There's something called Jeffrey's prior, which is a particular choice of prior that is meant to cure this prior dependence. And what it will lead to most of the time, it will be to posterior distributions on these kinds of parameters that are almost completely flat, basically telling you that your data doesn't really tell you anything about these parameters, basically. Yeah. Yeah. Okay. It depends on what you know about your data. So if this is a power spectrum, right, where you can assume that the map is Gaussian, then you should do a map a map likelihood rather than a power spectrum likelihood. Or if you know that your map is Gaussian, then you can account for the fact that the shape of the distribution is actually not Gaussian. So you should write the generalization of that to a Wishart distribution, which is that curve, the red curve over there. It's a more complicated function, basically. Yes. Yeah. So in principle, the same logic should apply to the correlation function. The annoying thing about correlation functions, and one of the reasons why I don't use correlation functions, is that for a given theta, the correlation function receives information from lots of different L's, and some of those L's might be very low L's, okay? For power spectra, you know that all of these L's are actually uncorrelated with one another because of statistical isotropy. We saw that, right? So all of these L's and M's, they are independent variables. So you can know that for a given L, a large enough L, the central limit theorem will hold because it only receives contributions from an average of lots of different variables. In the case of the correlation function, surprisingly, even on relatively small scales, because you will receive maybe significant contributions from low L's, those will be non-Gaussian, and the correlation function might have a very non-Gaussian distribution. So sometimes you need to be careful with the correlation function. Yeah. Yep. In what estimator? Yep, that's true. Yep. So, right. So if because of masking, you will get mode coupling. So you should always look at your mode coupling matrix. Right. So this is MLL prime. Let's say this is L and this is L prime. Typically, unless your mask is completely messed up, this will be a very diagonal matrix with some off-diagonal elements, right? So that just tells you that, yes, you have mode coupling, but that mode coupling only applies to relatively adjacent modes, right? So that means that your different L's will not be very correlated, and that out of all these 2L plus 1 modes, Maybe not all of them will be completely uncorrelated, but most of them, you'll get the effective number of modes will be quite large anyway, so the central limit theorem still holds. If you have a mode coupling matrix that is very off-diagonal, then probably the central limit theorem, you need to be careful about it. It will depend on the mask, mostly, yeah. I'm going to push through, because otherwise we're not going to have time to go through the notebook that I wanted to show. So I'm going to ignore questions for now. All right. So, what I wanted to do in the second half of the lecture is basically go through a notebook, which hopefully you can see. Yes, that will take us from a real catalog of galaxies all the way to final parameters. Okay. And so this catalog of galaxies comes from a sample of galaxies called Quaya, which is a sample of quasars. And what we're going to do is we're going to measure the power spectrum of these galaxies, the cross-correlation of these galaxies with CMB lensing, and we will extract constraints on sigma 8 and omega m. This is real data, okay? I assume many of you are familiar with Python. So we start by loading a bunch of libraries. These are kind of standard things that you probably are familiar with, but I'll just point out a couple of useful libraries that you should become familiar with at some point. The most important one is HillPy, if you want to do anything with maps of the sky. So HillPy, anyone familiar with HillPy? Okay, right. So this is basically a Python library that allows you to handle maps of the sky, okay? Namaster here, called PyMaster in Python. This is a code that I wrote that allows you to compute power spectra, so it implements this method here. SAC is just it's a library that allows you to store power spectra. In fact, actually, we're not going to use SAC, so ignore that. And then AstroPy, we're going to use to deal with the catalog itself. So the catalog is in a file format called FITS. Anyone familiar with FITS? They're ubiquitous in astronomy, so it's common to come up with them. So the catalog is in a FITS file, and we'll use AstroPy to read those data. All right. Okay. So we're going to make maps in HillPy, and we're going to use a given angular resolution, and that's controlled by this parameter in HillPy called nside. So this will be about, I think it's about 5 arc minutes on a side. So each pixel is between 5, I think it's 5, maybe 10 arc minutes on a side, more or less. And we're going to calculate power spectra up to an L of 1,500. Okay? And this is just the number of pixels that we have. Just for reference, let's look at how many pixels we have. So we have 3 million pixels, right? If we wanted to actually compute the full covariance matrix of our map, that will be a 3 million by 3 million matrix that we cannot really store in memory. Okay? So that's why we don't do map level likelihoods. All right. So let's read the data. I'm going to read the data, and I'm going to limit our catalog to quasars with redshifts between 0.5 and 1.5. Okay? So that's what's going on. I'm just reading a catalog and then removing all the galaxies that are below or above those limits. Okay? And then I'm reading a mask as well. So this mask, let's plot it. This is what the mask looks like. Anyone tell me what that thing is? That's the Milky Way. Yeah. So that's the Milky Way in equatorial coordinates. Sorry? It's the coordinate system that we live in. Yeah. So this is in equatorial coordinates where the equator here is the Earth's equator, right? So that's why the galactic plane looks weird. Right, so what this mask is telling you is what is the effective area of each of your pixels, right? So if you're counting galaxies in each of your pixels, you should account for the fact that this pixel counts almost as 1, right? But these pixels here don't really count that much. And the reason is that you have a lot of extinction, for example, close to the galactic plane. So this is accounting for extinction, right? Okay, so now we have our catalog. And what we're going to do is construct a map of the overdensity field. So for that, first, we make a map, and let's plot that map. So this map will be the number of galaxies that we have in each pixel, okay? And then what we need to do is we need to calculate delta. And delta would be the number of galaxies in that pixel divided by the expected number of galaxies in that pixel right, the mean, minus that mean. And that's what's happening here. But if you see what's happening here, what I've done is I've taken the number of galaxies in a given pixel and divided by something that depends on my mask, right? But that's because I need to account for the fact that in a given pixel, I can only use a part of that area, right? So I should account for the fact that there should be fewer galaxies in that pixel. So that's why the mask features here in the denominator. So let's plot that as well. The mean is over the, right, so what I've done first of all is I've thrown away all the pixels where the effective area is smaller than 50%, just to make sure that any kind of crappy pixels, I just throw them away. So that mean is calculated only over the pixels that survive that cut. So you can't probably see very well because it's a bit far away, but this is the number counts map, and we have pixels with galaxies between 0 and 5 galaxies, right? You can, if you squint, because the color scale here is not very good, you should see that we see fewer galaxies towards the galactic plane than we see away from the galactic plane, right? It kind of becomes darker the closer you go to the galactic plane, and this is just because it's tracking this plot here, right? The extinction. And here's the overdensity map. I'm going to do something which is this. Right, no, let me do something else. Okay. Mask G. Right, so this is the same map as before. This is the overdensity, and the gray area is everywhere that the mask is exactly 0, right? And if you squint enough, you'll see that actually the distribution of the density field now looks kind of homogeneous, right? You see the same level of variation kind of across the whole unmasked stuff, and that's because we've corrected for the effects of dust extinction, right? Okay, so now we have our map of the galaxy density, or the galaxy overdensity. To develop a theoretical prediction for the power spectra, remember that we need to calculate the redshift distribution of this sample, okay? This is a sample that has photometric redshifts. And for this sample, and as an exception, we actually have a probability distribution for the true redshift of each galaxy given its photometric redshift. Okay, and this is not common, and in fact, I don't trust this probability distribution very much for this catalog, but we're gonna use it, okay? And so what that means is that I can calculate the full distribution by just stacking this distribution for each of my galaxies. So I'm going to take all my galaxies, I'm going to evaluate this probability distribution, I'm going to add them all together, and that will give me the global probability distribution for my galaxies. Does that make sense? I don't see any nodding, which means that it doesn't make sense. Okay, well, I'm just going to do it and plot you the result, and you'll see. It takes a while because it's actually stacking lots of probability distributions, but the result is this, right? So this is the P of Z that we saw in the first lectures. And remember, we took galaxies between redshift 0.5, which is around here, and 1.5. So why do we have these tails? Say again? Yeah. Exactly, because what we can measure is the photometric redshifts, and that's how we have sliced our sample. But what this is showing is the distribution of the true redshifts, and those are different. There's tails due to the photometric redshift errors. All right. Great. Okay, so now let's try, well, we'll start computing power spectra soon. And for that, yep. That's just the distribution looks like that. There's a bit of a bump in the distribution of quasars in this sample. Yeah. You know, it depends on how you have selected these quasars, right? You have a map of the sky. You try to select targets that look like quasars. You do some selection on their colors, and sometimes that can lead to these kinds of things. Yeah. It's not weird. This is a very well-behaved redshift distribution. Yeah.
So when you selected this redshift range, you use the photometric redshift?
Yes.
Selected range.
Yes, because I don't have true redshifts for most of these objects. Yeah, so I can't really select them by true redshift. Yeah. All right, so when we compute the power spectrum, we're going to need to compute the spherical harmonic transform of our map, and that's what Namaster does. So this command here, what it's doing is computing that spherical harmonic transform and storing it in an object called an NMT field. Okay, so that's all that's happening. And it's quite fast, right? For this pixelization, you saw it didn't really take that long to take a spherical harmonic transform. So it was, yeah. Okay, we said that we're going to look also at the cross-correlation with CMB lensing. So I'm just going to read the CMB lensing map. And this has come to us, let's say, as a map already, okay? In reality, it hasn't, because this map is provided by the Planck collaboration in a different way. So I've already pre-processed it to make our life easier. But, you know, so the only thing I'm doing here is I'm going to read the CMB lensing map and its corresponding mask. And let's plot them as well. And this is roughly what it looks like, right? So this is the map. The kappa map is just noise, because it's actually noise dominated. And this is the mask for the kappa map. So this is based on Planck, where what they do basically is they cut regions of the sky depending on how strong the galactic contamination is, and contamination from extragalactic point sources and things like that. So that's all the holes that you see here are basically extragalactic point sources that could mess up the lensing reconstruction. Yes? The what? This? Or the previous one? So this is just the thing that will store all the information about our maps and the corresponding mask and the spherical harmonic transform of both of them, of the mask and the map, basically. So when I call this, what I'm doing is I'm computing the spherical harmonic transform of the mask and the map, basically, and storing them inside there, right? So I'm not showing you the guts of how that happens, but this is what happens behind the scenes in the code, right? Okay, so we have two fields, the kappa field here and the galaxy field, and we're going to look at their cross correlations, right? And the autocorrelation of them. All right, so we're going to look at cross correlations. We could do that for all L's, but that's going to look super noisy. So what I'm going to do is I'm going to calculate the CL at all integer L's, and then I'm going to do averages in bins of L just to reduce the noise a little bit. So that's what this structure here does. So I'm going to go all the way to L max of 1500, but I'm going to bunch those L's up in groups of 30, right? So we'll have what we call band powers of 30 L's by 30 L's. That's what's happening here. And then this is where we calculate the power spectra, okay? So let's look at these three lines. These are the three lines that we use to calculate the power spectrum of the galaxies. The first one, called compute coupled CL, what it does is it just calculates this thing. It's called the coupled CL because this has mode coupling in it, because it contains, you know, it has all the mode coupling caused by the mask itself. The second line, can you see, or should I make it larger? It's okay. Okay. All right. Sorry? Yes? Okay. The second line, which spawns this thing called the workspace, what it does effectively is calculate this mode coupling matrix. Okay? So we have this bit. This is the coupled CL. We have this bit. And so the last line, what it does is to decouple that CL. So effectively, it inverts the matrix and puts it on the other side so that we can get the true CL out, okay? So we're doing that for the GG power spectrum. We're doing that for the G kappa power spectrum. I'm also doing it for the kappa kappa, even though we're not going to look at it. And the reason is that we need that to compute the covariance matrix. Ask me about that later. Otherwise, ignore this line. But this is the data that we're calculating, right? Yes. Yes. All right, so we also need to calculate the covariance matrix, and I haven't explained to you how that is done, and I'm going to not explain it to you. And we can talk about that in the Q&A if you want, but that's what's being done here. And it will take a little bit, but because this is actually a relatively slow step, but you'll see that it's nothing too complicated. So it'll just take like maybe 10 seconds in total. All right, so we've computed the covariance matrix, and now we're going to look at the structure of that covariance matrix. This is what the covariance matrix looks like. So you have the covariance matrix for the measurements of the GG power spectrum in this upper left block, the G kappa power spectrum on the lower left block. So you can already see that our measurements are quite uncorrelated across different multiples because this covariance matrix is really diagonal, right? We have these off-diagonal elements here, which are the correlations between CLGG and CLG kappa, because they both sample the same part of the sky, so there should be some correlation between them. But yeah. 30. 30. There's 50, yeah, so there's, in total, there's, yes, exactly, yes, yeah, yeah.
So the first 50 is...
First, that's right,
the second 50
is G kappa, yeah. We're going to look at the data now in a second. So let's look at the data. This is what the measurements actually are. We haven't looked at those yet, but all right. So we have the red points. That's the cross correlation between galaxies and CMB lensing, right? And then you have the galaxy autocorrelation, which looks kind of weird, right? Whenever we've plotted power spectra, we always plotted them like this, like things that does something like that, right? They decay, and the cross correlation kind of looks like it's decaying, so that's kind of nice. But what's happening with the galaxy autocorrelation? Why is it just like that? Shot noise, exactly. Yeah. So this catalog of quasars is very sparse. So the density of it is quite low. So the shot noise amplitude is quite high, right? So what you're seeing is, if this was CLGG, and this was the signal part that we care about, the shot noise is for quaya. The shot noise is like this, basically. So you're just seeing the shot noise, really. All right, so we need to subtract that. And we said that the shot noise, this thing was just 1 over the number density. So let's just compute that. So we calculate the number density here. And this is a tricky part, because the number density in our case is not homogeneous across the sky, right? We have a spatially varying selection function. So you need to implement this correction here in order to account for that, the impact of that selection function. So if you had perfectly homogeneous mask, right, this would be mask squared would just be either 0 or 1, and mask would be either 0 or 1. So this correction factor would be 1. But if you have inhomogeneities, you need to account for that. And it's through this factor, I can give you a reference for the math of that. So what I'm going to do is I'm going to plot the same thing, but now I'm going to add a line where we have predicted the shot noise should be. And we see if it agrees actually with the data. And it does, right? So this line here is what the shot noise should be, and it converges to the high L power spectrum. All right, so let's look at the actual data we're going to analyze, which is the black points subtracting the shot noise. Okay. All right, so that's the actual data we're going to use. And that looks better. That looks like at least like a function that goes down with L, which is what large-scale structure usually looks like. All right, so this is the data we're going to use to try to infer omega m. Sorry, we're going to try to infer sigma 8. Okay. The rest of the notebook is doing that, is doing the parameter inference. So I'm going to stop here. Any questions about what we've seen so far? Say again? Yep. They don't change because you know exactly what shot noise is, so you can always subtract it analytically, basically. Yeah. Other questions? We are not going to use CLKK for several reasons. So the main reason is when you measure kappa from CMB reconstruction, what you're measuring, the measured version of that is the true underlying kappa with some noise as well, right? Let's call that N kappa. And remember that the way we reconstruct kappa is by looking at different correlations of the temperature fluctuations, right, at different multiples. So it's a quadratic estimator. So this noise here is the residual kind of 4-point correlator of the temperature fluctuations themselves with noise from Planck and blah, blah, blah. So this is very much not white noise, and it requires some careful modeling in order to account for it properly. And that will appear in kappa kappa, right? This will not correlate with galaxies, so that's why we don't care about it in the cross correlation. But in the autocorrelation, you will see it there, and you should subtract it, and that's tricky to do. Yeah. But people do it. I'm not an expert on that, but so Planck have papers, obviously, where they have used the kappa kappa power spectrum to constrain cosmology, but it's more complicated than what we have time to do here. Yes, so what I'm doing is so imagine that you had perfect redshifts for all your galaxies, and you had to construct the redshift distribution. You would just add all your galaxies up and construct a distribution for them, right? So you just do a histogram of those redshifts, and you're done. In this case, we don't know the exact redshift, but what we know is their probability distribution for those redshifts. So what I'm doing is just I'm adding each galaxy in, but instead of each galaxy being a delta function, it's basically a blob with that distribution. So I'm just adding all of those together. Yeah. Say again? Yes. Yes, exactly. Yes, yeah. Other questions? No. So the idea is we have two fields, right? We have the overdensity field, delta G, and the measured version of that is just the true underlying smooth density field plus the contribution from shot noise. And the kappa field, as we said, is the same structure. So kappa is the true kappa, and the noise from reconstruction. Noise from reconstruction will depend on the CMB fluctuations, and it will depend on the noise, the instrumental noise of Planck, or the Planck satellite. And this is just shot noise of the galaxies. This should not correlate with this at all, right? This comes from completely different data sets, has nothing to do with one another. So the cross correlation between these two fields, which would be in principle be the cross correlation of these two, the cross correlation of these two, the cross correlation of these two, and the cross correlation of these two. Out of all of those, the only one that is non-zero is this one, right? Because the other ones are not correlated with one another. Yeah. Why should it decay? Remember that the CL is a Limber integral d chi squared of blah, blah, blah times P of k equals L over chi, right? And the P of k decays, so CL will also decay with L, right? Yeah. For large-scale structure. Yeah. Okay. So let me actually write this properly, because we're going to need it now if we write theoretical predictions for these CLs. So the CL GG is integral along the line of sight of the kernel for galaxies squared times P galaxy, right? P of k equals L over chi, comma Z. And then CL G kappa is going to be equal to the same thing, QG of chi, and then the lensing kernel, remember, QL of chi. And then the power spectrum P of k equals L over chi, and Z. Okay, so we need to write theoretical predictions for these two. Remember that we're going to assume a very simple model where the galaxy overdensity is just a linear bias of the matter overdensity. Okay, so that means that this power spectrum should scale. If this is the matter power spectrum, we should include 2 powers of the galaxy bias, and for this one, we should include 1 power of the galaxy bias. Yes, does that make sense? All right, so this is going to be our model. Okay, so to make all our theoretical predictions, we're going to use this package called the Core Cosmology Library, CCL, which apparently Rogero is a big fan of, and I didn't know. So it's a Python package that allows you to do theoretical calculations in cosmology. So we're going to start by creating an object called a cosmology object. So it's just the object that will contain all the information about the cosmological parameters that you have, the linear matter power spectrum, the non-linear matter power spectrum, things like that, pure cosmological quantities. Okay, so that's what's happening, and I'm creating an object called vanilla lambda CDM, and that's because this is going to be a vanilla model with omega m equals 0.3, sigma 8 equals 0.8, the usual kind of lambda CDM parameters, okay? Great, and now we need to compute this, as we said, this type of power spectra, right? Things that are integrals of the product of two radial kernels and then the 3D power spectra. So we're going to need the radial kernels for galaxies, which depend on the redshift distribution, and then the radial kernel for kappa. And in CCL, those you can calculate automatically by creating objects called tracers, and these tracers are basically containers for these radial kernels. Okay, so we're going to create one for the galaxies, and the name of the tracer for galaxies is weird because it's called number counts tracer. It's just galaxy clustering. And you can see that we need to pass it the redshift distribution of our galaxies in order to calculate it. And I'm going to assume bias 1 because I'm going to multiply by the bias at the end. Okay, so that's the galaxy bias. And then this other tracer is just the CMB lensing tracer containing the lensing kernel for sources at redshift 1100, so at the last scattering surface. Okay, so I just execute that, and that will store those. And now I can generate predictions for the galaxy and galaxy kappa power spectra by simply calling this function in CCL, which basically takes these two kernels. It uses the matter power spectrum that CCL has already computed, and then it gives you the corresponding CLs. And you can sample them at whatever Ls you want. These are the Ls at which we have measured the power spectra, so that's what I'm using. Okay? All right, so that's what it does. It doesn't take too long. Okay, and now let's plot the result. But remember that these power spectra, I calculated them assuming bias equals 1, and we know that bias is not 1. So I kind of know what the bias of these galaxies is because I've used them in the past. I know it's about 2. So what I'll do is I'll take the theoretical prediction for GG, I'll multiply it by bias squared, G kappa multiplied by bias, and let's compare that with the measurements, right? And look at that. That's kind of nice, no? So if you look at this plot, what things would make you suspicious? This first point, right? So this is the impact of residual systematic in the data, right? So this is, we know that in Quaya, we still have some residual systematic contamination from something in the sky that we haven't been able to remove. So this point is affected by that, and we're going to remove it from our analysis. So basically, I'm going to remove all the data from L equals 20 and below, so that I'm not affected by those systematics, okay? I know that there are no systematics beyond that L because I know that all of these other measurements in the actual analysis were really robust to the way in which we account for systematic uncertainties, whereas this point actually moves all the time depending on how we deal with systematics. So all the other ones don't. So that's why I know that this one is the dodgy one. Okay. So now, any questions? Because in our measurements, remember at high L, they were dominated by shot noise, right? So the fluctuations due to shot noise are quite large at high L. Once you've subtracted the shot noise, you still have the residual error from that. And here you have a similar picture, except this is a mixture of shot noise from the galaxies and noise in the kappa map. And both of them are quite large at high L. So that's why the error bars are quite high. Yep. So CCL has functionality to have nonlinear bias with the same parameterizations that we saw that you saw in Roman's lectures. So those exist. But I'm not showing you how to use them. It's a bit more involved to use. Yeah. You can, so in that case, you would need to play tricks, right? You would need to compute the contributions to the total CL coming from all the different bias terms, and then each of them, then multiply them by the corresponding biases, and then put it together yourself, basically, right? Yeah. Say again? Well, so the CLG kappa itself is not subjected to noise. Like it doesn't have any contribution, as we said, from this correlation, because these two things don't correlate. But they contribute to the uncertainties in the CL, right? They will give you statistical variations in the CL that will average around 0, but they will still be noise. So that they contribute to the error bar, but not to the mean of the estimator itself. Yeah. Okay, so now what we were going to do is we're going to sample the distribution, the posterior distribution of our data. We're going to assume a Gaussian likelihood like this, and we need to write a model. So our model is going to be what's our model going to be? So we have computed this power spectra for bias equals 1, and for sigma 8 equals whatever it was in the cosmology that we selected, so sigma 8 equals 0.8. And so how should our power spectra actually depend on bias and sigma 8? So we've computed these ones for fixed sigma 8 and fixed bias. We've already said CLGG should go with bias squared, and CLG kappa with just bias. And then the dependence on sigma 8, if we were looking at linear scales, the power spectrum is proportional to sigma 8 to the power of 2. We said that. Everyone happy with that statement? Yes? Okay, so what we're going to do is we're going to take our theoretical prediction, divide by the fiducial value of sigma 8 in the cosmology that we created it for, and then multiply by the value of sigma 8 that we're trying to infer. Okay? So our model is going to be very simple, just two free parameters, B and sigma 8. This is not what we will do in the real world. We would have many other parameters to account for many other things. And this is our model. It's super fast to evaluate because we just need to multiply by bias and sigma 8 a bunch of times. All right, so, yep. Yes, good point, sorry. I just realized that I skipped that. So, as we said, we can only use linear bias and also this assumption of linear growth where sigma 8, sorry, the power spectrum is just proportional to sigma 8 squared on large scales. So I'm going to impose some scale cuts. First of all, we said we're going to throw away all the L's below L equals 20 because of systematics, but then I'm going to throw away all the large L's, all these ones, because we want to stay within the linear regime, okay? And effectively, I know that works up to the BAO scale, more or less. Remember, the BAO scale is at 0.1 inverse megaparsecs. So I'm going to relate K to an L, right? Remember that the corresponding, if we have a given K max, so the maximum mode up to which we want to do the analysis, we can relate that to a maximum L max by just multiplying this by the mean distance to our galaxies. So I'm going to take the mean redshift of all these galaxies, calculate the distance to that redshift, multiply by K max, and that will tell me what the maximum multiple is that I can use. So if you see, that's what's going on here, right? So I take the mean redshift of my sample, calculate with CCL the corresponding moving distance, multiply both of them, and that tells me what L max is. Let's print L max so that you have an idea of what that is. Then the rest of what I'm doing here is I'm just preparing my data. So I'm taking my measurements, restricting them to these scales, and then concatenating them into a full data vector. And I'm doing the same thing for the predictions, for the templates, sorry, these templates here, the TLGG and TLG kappa for the fiducial cosmology. And then that's it, basically. And then doing the same cuts on the covariance matrix. So this is just bookkeeping. So we're only going to be able to use data up to an L of 360, right? So that means we'll be throwing away all of this stuff here, and also these first 2 points. Okay? Does that make sense? Questions? Okay. Great. Now we create a probability distribution, right? The posterior distribution. We said we're going to use a Gaussian. So that's effectively what's going on here. I'm going to try to zoom in a little bit. So this function, chi-square, just contains this bit. This is what we call the chi-square of our data with respect to a model, right? So what have I done? I compute the theoretical prediction by scaling the templates with bias and sigma 8, as we said. I'm subtracting that from the data, and then I'm doing that difference between CLs, dot product with the inverse covariance matrix, dot product with that difference again, right? Does that make sense? Yes?
So it seems that you are doing the normalization of the.
Mm-hmm. Yeah.
It is purely
The normalization of what?
of the distribution.
Of the Gaussian, yes. So what does the normalization depend on? In principle, it depends on, it would be 1 over the determinant of the covariance matrix. So your question is whether the covariance matrix depends on parameters, I guess, or not.
Could happen that it make it weird at some point. Or
So, all right. The statement is that if you're using this trick where you use a Gaussian likelihood for your CLs, it's actually incorrect to assume that your covariance matrix still depends on parameters. So that's mathematically, that's the answer to that question, is you should not account for parameter dependence. The less controversial statement is, even if you did, it turns out you can show mathematically that the amount of information you're going to get from this is going to be tiny, tiny, tiny. You don't get much compared to the information encoded in the mean itself. And we have a paper showing that. I can show you the paper. Okay. All right, so that's the chi-square. And then what we do is just calculate the log probability. So you just multiply by minus 1/2 here. And many of these sampling codes, like the one that we're going to use in a second, they use you don't give them the probability distribution, you give them the logarithm of the probability distribution. So that's why this is what we're calculating. We're almost there, just 2 minutes. Okay, so first, let's try to find the best fit of our data, meaning the quantity that maximizes this likelihood or this posterior, right? So I'm just going to use this minimizing function, which actually is maximizing, from SciPy to get the best fit value of the parameters. And let's plot them, let's print them. So it was super quick, right? Because our likelihood is very simple. And it tells us that the best fit value of the bias parameter is about 1.86. And the best fit value of sigma 8, we're in luck, is 0.8, which is kind of what Planck likes, right? So that's kind of nice. Okay, so that just gives us a single point, the maximum point of the likelihood. And now let's sample the whole thing. And for that, we're going to use this package called MC. So MC basically implements a version of the Metropolis Hastings formalism that we talked about before, right? So I'm going to run a chain with 10,000 samples. So we have actually lots of samples to do statistics with. And you'll see that it doesn't take too long. So that's how long it took to sample 10,000 samples, right? This is only because our likelihood is very, very simple in this case. In general, this would be much slower, which Paco can tell you, because he's been trying to do this. Right, okay, and now there's this other package that you should probably at some point become familiar with called getDist. And getDist is just a very nice way to analyze MCMC chains and get posterior distributions on parameters and things like that. So I'm going to take this chain and I'm going to plot it. And these are the constraints that you get on bias and sigma 8, right? Yeah, so these are the typical contour plots that you'll see, where each contour there tells you about the 68% confidence level, the 95% confidence level. Yeah, and those are the constraints. Okay? Any questions? Yes? Yeah. Mm-hmm. Yeah. So finding the minimum of a multidimensional function is complicated because it depends on where you start. The fastest methods are the ones that use derivatives. And I think Paco has told you, must have told you something about minimizing in large parameters, because that's what machine learning is all about, right? So the optimal method is something called the Newton-Raphson descent, but can be computationally a bit jittery to implement. And it will still have the problem that if you start in a region close to a local minimum or maximum, you'll end up there. So often you just need to use your judgment, maybe start several minimizers at different places and see if they all converge to the same minimum or not. So it's, yeah, it's complicated. You can never be completely sure, but yeah, yeah. Yes. Yeah. Yeah, exactly. No, and this is a problem, especially if you have a very complicated likelihood that depends on thousands of parameters, you should worry very much about this, for sure, yeah. Okay, that's all I wanted to say, so let's stop here. Maybe there are other questions afterwards. Yeah, thank you. Everyone's very sleepy. I feel like maybe you guys went out last night or something like that.
Very quick question. When
Yes.
you computed the galaxy over density, you corrected the mean density by some factor of the mask.
Yep.
Can you repeat that?
Yeah. I mean, the idea is the following, right? So what I said is that my mask, which I called W before, in a given pixel P, what it tells me is basically the effective area of that pixel, right? So what that means is that if I'm counting galaxies in the sky in different pixels, and WP is 0.5, that means that actually for this pixel, where WP is 0.5, I should assume that I could only access about half of the area, right? So if the mean number of galaxies is X, then the local mean here should be just X over 2, basically, right? So that's all I'm doing. It's for the local, in each pixel, I'm just accounting for the fact that maybe the effective area in that pixel was smaller. So then you should correct your mean by that amount, basically, yeah.
So I wanted to ask, like, if the problem had like a small amount of data, like a few thousand, would you still prefer this approach?
No, if you can do a map level likelihood and you're certain that it's a Gaussian map, the map-based approach, it will give you the right thing, and you should use it.
Okay,
yes.
and why can't the covariance matrix, or why shouldn't it depend on the parameters?
It, in principle, does depend on the parameters. In practice, the point is that we're doing an approximation when we use that likelihood, right? And the approximation is that we start from a map level likelihood, and then we write an effective likelihood for the CLs. And you can compute do you know what a Fisher matrix is? All right, the Fisher matrix basically is a matrix that essentially tells you what is the maximum amount of information that you could get from a given likelihood, from a given probability distribution. Okay. So let's say that you take your map level likelihood, the one that you know is correct, and estimate the Fisher matrix. So that should tell you what's all the information that you can gather from this likelihood. Okay. Then you calculate the same Fisher matrix for the effective CL likelihood. Okay. And you can do it in two versions, where that effective likelihood, the covariance doesn't depend on parameters, or when it does depend on parameters. And what you see is that if you assume that your covariance matrix should depend on parameters, then the Fisher matrix is actually more informative than what it was in the original map level likelihood. And that cannot be, right? Because the map level likelihood already contained all the information. So it cannot be that your effective CL likelihood. And so you can see actually that, in fact, both converge to the same Fisher matrix if you assume that the covariance matrix is just it's parameter independent and evaluated at the true cosmology, basically.
Yeah, so I would like to know if the pixelization that you did with HillPix affects higher Ls in this analysis?
Yes, it does. Yes, exactly. Yeah. Yeah. So, right. How can we think of pixelization, right? Let's say, imagine that you have a map of some quantity with infinite resolution, right? Let's call that the ideal temperature map of the CMB, which has infinite resolution, right? What would be the value of the temperature at a given pixel P? Now with finite resolution, it would be something like the average, right? It would be something like integrating over points in the sky within this pixel, right? Of T of x. Sorry, I'm not sure why I wrote n here. Let's say x, right? Within the pixel. So times, for example, the pixel window function. So this is something that is 0 if you're outside of the pixel, or 1 if you're inside the pixel, right? So this is essentially, at each pixel, you're averaging your signal within the area of that pixel. And so this is for that particular pixel. So what is product in, sorry, this is actually a kind of a convolution in real space, right? This becomes a product in harmonic space. So what you'll see if you have pixels is that your CLs, which should have been like this, they'll be further suppressed like that. And that's because in harmonic space, you should multiply your theoretical predictions by the harmonic transform of your pixels, basically, right? Because this convolution transforms into a product. So essentially, this is just saying that all the small scale structure, you're kind of washing it away by doing this averaging into pixels, right? So we haven't worried about that because we were cutting at L of 360, where that didn't really matter, but otherwise we should have accounted for that effect.
Okay, I'm not sure if we have time or maybe on QA, but I would like to know more about the covariance matrix.
Q&A, yes.
Okay. Yeah, so David will be here for the Q&A this afternoon.
Yeah.
And also, he's going to upload, or we are going to
yes.
Upload this notebook and all these slides. So let's thank David for this excellent set of lectures.
Thank you.